Alright, for the time being, this is likely to be the last video I post for now on vector word problems. There are a wide variety of them that can show up. My goal with this last one is just to show you that sometimes they'll provide you with a slightly different way of measuring an angle. So the last couple videos I posted had angles that were assumed to be measured from the positive x-axis and in a counterclockwise fashion. I've shown in previous videos that you can measure using things like northwest and northeast. You can say things like east of west or east of north and east of south, that kind of thing. This problem is a little different because I use this word bearing. And you'll find that if you go out into the world and you look at different fields of study, if you look at different ways of measuring, you'll see that depending on what you're looking at, for example, this is nautical, we're talking about a yacht cruising at 20 knots. In a nautical setting, they might use bearings instead of your traditional x-axis mentality. A lot of things will measure from a northern axis as opposed to an eastern axis. And so what I mean by that is that if I'm thinking about our cardinal directions, north, south, east, and west, when we measure bearings, instead of starting on the eastern axis and going counterclockwise, we actually start on the northern axis and move clockwise. So this is how we move when we deal with bearings. And that feels a little weird, it feels a little wonky, and it will cause problems with my way of solving vector problems. I like to break things into their component forms. In order to do that, I need to know what angle they're actually being measured at from that positive x-axis and counterclockwise. We're going to find it's not that big of a deal though. What I want to do is take a look at my angles for this problem. So the yacht is cruising at 20 knots with a bearing of 185 degrees. So let's go ahead and think about what that would look like. I have my north, south, east, and west set up here. A bearing of 185, well 180 would be two quadrants like this. So 185 is just a little bit past that. I'm looking at a vector that would be pointed in this direction. And in fact, this little angle here, this little tiny angle that I'm marking here with these triple arcs, that little angle is a 5-degree angle. How do I know that? That's the question you should ask. I know that because this total big angle here for this vector is 185 degrees. So if I kind of chop out these two sections here, these two 90-degree sections, that full 180 gets pulled out of that 185, and that tells me that this right here is 5 degrees. I can use the same kind of logic now to create the angle that I actually want in here. So I want this angle that I've just drawn, starting on the positive x-axis and moving counterclockwise. So again, we see 90 and 90, so we got a nice 180 for the first two quadrants. And then I want to ask, how much of the third quadrant am I actually using? Each quadrant represents 90 degrees, and I'm shaving off this 5-degree section here. So my theta angle for that first part for the yacht looks like it's going to be 180 plus 85. So that's going to be 265 degrees. You could also think of it as 5 degrees short of the full 270 degrees. If you want to think about it that way, that would have been faster probably. So I know that the theta for my yacht, let's put a little, y might not be what I want to put here. Let's say B for boat. Let's call it a boat. So the direction for my boat is actually 265 degrees. Well now, I want to do the same thing for the wind. I want to think about the wind for a moment. It says the wind is moving at a bearing of 290 degrees. So we have 90, we have 180, we have 270, and then 20 more degrees past that. This is where I would end up if I was the wind. And so you can see here, if you think about it, if this is the direction the yacht is heading and the wind's blowing this way, you can imagine the yacht's going to veer off course just a little bit. It's going to be blown off course. What we want to do now is say that this little shaded region is that 20 degrees I mentioned. It's the 20 degrees past this 270 part. That's how we get a total of 290. So this little region here is 20 degrees. That means my actual angle, this guy here, my actual angle is going to be 20 less than the 180. this is going to be 160 degrees. Let's call that W for wind. So our theta for wind is going to be 160 degrees. So we've set this up now so that we can work with them as if they had provided us with an angle from the positive x-axis and counterclockwise. Now that we've done that, everything else about this problem is the same as it's been in pretty much every other example. I want the resultant speed and direction, that's magnitude and direction. So I'm looking for the resultant, the combined force. So what I'm going to do is, let's just say vector B and vector W. I want to find what B plus W equals. So that's really what they're asking me now. Just like in the last video now, we can find Bx and By, we can find Wx and Wy. And once we've done that, we'll be able to go in and easily figure out the resultant speed and direction. Now, Bx, this is for the boat. The yacht was cruising at 20 knots. So I want to jot down the 20. And we had a 15 knot wind. So we're going to go and drop our magnitudes down here. X and Y always correspond to cosine and sine. So we're going to see that repeat in the pattern here. And then in the parentheses for our cosines and sines, we're just going to input those angles that we just found. We found that our theta for B was 265 degrees. That was for our boat. We'll drop our 265s in those parentheses. And then the angle, our direction angle for the wind is 160 degrees. I'm being a little inconsistent by not writing the degree symbol every time, so there we go. We're going to go ahead and find out that these guys here are easy enough to find by grabbing our handy-dandy calculator. So our x component of our combined vector we'll get by taking this x component. This is the x component of our boat. We're going to add to that the x component of our wind. Now, you may look at that and go, oh, so wait, but it's negative. Like, how does that work? It's speed. This is supposed to be about speed. Well, remember, this is saying that it's negative because it's thinking it's moving westward, essentially. The negative here for the x component means to the west, where a positive would mean to the east. So this is okay to be negative. Let's call it negative 15.84. I'll put another comma there because I'm not thinking. And real fast, let's go and do what we did before. Oh, I hit enter twice by accident. We're going to go and replace the cosines with sines just so we can get the y component version of this. And easily enough, we see negative 14.79. And when you look at that, you may go, okay, well, they both turn out negative. I want to make sense of whether or not that's reasonable. I personally think so. I think in a problem like this, while a wind can have a heavy impact on a particular object, especially out on the water or in the air, you also expect that the yacht is going to be able to go kind of in the direction it's wanting to head anyway. So our yacht was heading in a negative direction. The wind came in and sure, it might blow it way off course. It could be a large chunk, but we're not expecting the wind to completely turn the yacht around and send it in another direction. That seems a little unrealistic. So if this problem's at all reasonable, we would expect that it stays both negative here. Now, as far as magnitude and direction are concerned, it's going to mean two things. One, the magnitude, we can just use the Pythagorean theorem, but the direction, we're likely going to be given an angle that falls in the first quadrant when we do this in our calculator, because it's going to divide these negatives out, and it's not going to realize that we're supposed to be in the third quadrant. So we'll just have to add 180 degrees to whatever angle the calculator gives us so that we end up in the proper quadrant. Having said that, let's go ahead. Hopefully I won't have to write this down every time now that we've seen quite a few examples of this. Pythagorean theorem, these are both the legs of a right triangle, and if you square them, the negatives do not matter. So this is just applying the Pythagorean theorem, and we see that our magnitude is going to be approximately 21.67. And our theta should be inverse tangent of our y component divided by our x component. By the way, seeing that these two are very close in size, they're very close together in magnitude, we would expect that we should get an angle somewhere around the 45 mark. It's not going to be exactly 45 degrees, but it should be kind of close to it. You'll notice that I dropped my negatives off of both because I just talked about how a negative divided by a negative is just going to be a positive. So when I input this into the calculator, let's be honest here, I like to save myself a little bit of typing if I can, and we're getting about 43 degrees, which is pretty close to what I just said. If I said it would be close to 45. So what we've done then is we've come up with a situation where our resultant vector, let's just call it R, our resultant vector would have a magnitude of 21.67 knots. I'm just going to write the word knots out here since that's what they did. And it's going to be an angle of 43 degrees. But if you stop here, if you box this in, you go, okay, I've got the unit there, I've got it written in direct notation, I've given speed, I've given direction. I will tell you, one, you're not done because we skipped moving to the third quadrant. And two, they didn't give us their angle measured this way. They didn't measure angles from the positive x-axis. So first, this 43 degrees, we would want to add 180 to that. So we're going to see 223 degrees is what we should have been working with. But we're supposed to be talking about this as bearings. So let's take a second and think about what that means. 223 would be somewhere out here, almost in the middle. But we want the angle to be measured here instead. So we know that this angle is 223 degrees, and we want to know what is its bearing instead. Well, there's some good news here. Because we already know that this little part here is 43 degrees, and we know that because this is 180 plus the 43, because this part is 43 degrees, this part down here must be 47 degrees. If this is 47 degrees, then I just have to add that to 180 here, and I'll have 90 plus 90 plus 47, and that will give me my sum total of 227 instead. So we actually want to say R equals 21.67 knots, and I'm going to specify at a bearing of 227 degrees.